Hi everyone. So today our topic of discussion is dual nature of radiation and matter. So let me introduce first. I am Shuvadip Ghosh. I am doing PhD in chemistry department IIT Kanpur. So I am a PMRF scholar. So that's why I am doing this course. Now let me start our discussion. So our topic is dual nature of radiation and matter. So now first we have to understand about what is radiation and what is matter. We are very much familiar with two things. One is matter. Matter actually, we are very much comfortable with matter because matter has mass. We know, we can see around us, there are lots of matters. And radiation, or 1 minute, radiation. Radiation means we can think like light. Light, light is a form of radiation. So matter and radiation, these are two fundamental things we can feel around us. Matter and radiation. Okay. Now let us start our course. Okay. We'll discuss first historic development. How our this dual nature of radiation matter has been identified. Basically, the photoelectric effect. Photoelectric effect at 1905. In that case, first through photoelectric effect, this dual nature of radiation and matter was identified. So before photoelectric effect, how the physics evolved, we'll discuss first the historic development. After that, we'll discuss the photoelectric effect. First, we need to discuss the historic development. Okay. Now we are very much familiar with the cathode ray. What is the cathode ray? Cathode ray was first identified by William Crook. William Crook at 1870. First cathode ray was identified. What is the cathode ray? Cathode ray is, let us consider, okay, this is some discharge tube like this. This is a discharge tube. So here two electrodes are there, cathode and anode. We know that cathode is negatively charged and anode is positively charged. So this is cathode, this is anode. And this is totally vacuum. This is vacuum. And this is a discharge tube. Now, if we give a higher voltage difference, what happens? Actually, we know that from higher potential to lower potential current flow. So this is the direction of current. But electron flows opposite to current. So electron will flow in this direction. Okay. So that means there is a lots of electron in the electrode of cathode. Here lots of electrons are there. Now when we apply higher voltage, what happens? Okay, now I should not utter the word electron, because up to that electron was not discovered. This is 1870. So now on applying the voltage, what happens? Flow of particles occurs from cathode to anode. This was the observation. And this ray was named as cathode ray because this ray is emitting from the cathode. That's why it is named as cathode ray. This is at 1870. Okay. Now after identifying the cathode ray at 1879, it was totally okay. At 1879, suggested that these rays consist the stream of negatively charged particle. These particles are actually negatively charged particle. We don't know what is this particle, but we can identify that these particles are negatively charged particle. That's why it is approaching through the anode. We know that anode is positively charged, and these particles are moving through the anode from cathode to anode. So this is the flow of particle, which is actually the cathode ray, and this is negatively charged, which was identified at 1879. After identifying the cathode ray, now J.J. Thomson. J.J. Thomson first was a British physicist who confirmed this hypothesis that this is a flow of negatively charged particle. Okay. So now, how we can identify the nature of the particle, because we don't know what is this particle. We are totally we don't know anything about this particle. We just know that this is a negatively charged particle. Applying a voltage different, higher voltage, these particles emitting from the cathode and approaching to the anode. Okay, these features we only know. Now we have to identify the types of particle, what is the particle actually. So now J.J. Thomson did an experiment. What type of experiment he did? Now let us discuss that first. Okay. So similarly, he also took like that. This is also a discharge tube. He also took. And similarly, here is cathode. Here is, now he put the anode here. This is the anode. This is like this. Okay. So now when on applying a voltage, what happens? Again the here is a window hole, and here is a, these are the detectors. Okay, he placed these detectors. These are the detectors. Also, one magnetic field and electric field also imposed. Magnetic field B is given, and electric field is, magnetic field is through the plane, perpendicular through the plane, and the electric field is in this direction. So perpendicularly, electric field and magnetic field was present. Okay, mutually perpendicular electric and magnetic field across this discharge tube. So then what happens? This cathode ray emits. This cathode ray emits. So now only through this hole, let's say one particle, because we know that this cathode ray is a flow of negatively charged particle. This particle is moves. Now after here, the particle is detected through this detector actually. That means the particle actually change its direction due to the presence of magnetic field. Now we have to just now identify that. How? We have, okay. So from here we can write half mv squared. What is m? M is the mass of that particle. This particle is emitting from here, that particle. V is the velocity of the particle. It should be equals to EV. Okay, not EV, it's QV. Okay, Q is the charge of particle, because we know that this is a negatively charged particle. Charge of the particle. Okay, V is the voltage difference between a cathode and anode, voltage difference. So this Q into V, this actually due to this voltage difference, the particle moves, and that's why the particle gains a velocity. So we can write this equation: half mv square equals to q into v. This is the kinetic energy, and this is the, we can say that this is kind of potential energy. Due to that potential difference, the particle gets accelerated, and that's why there is a kinetic energy. So half mv square is equal to q into v. So from here we can write q by m equals to v square by 2v. So here the small v is the velocity and capital V is the voltage. Okay. Now here we can see, due to this is the magnetic field B. Okay. Due to that magnetic field, this particle actually deviates. Okay. Now we know that the magnetic electromagnetic force actually how it's acting Q into V cross B. This is the Lorentz force, right? So force will act like this: F equals to Q into V cross B. So V in that direction V, and B is perpendicular through the plane. So if we see, then Fleming rules, it will deviate through this direction. Okay. So F equals to Q into V cross B. Now as V and B perpendicular to each other, so we can write that F equals to Q V B. Not considering the vector notation, because V cross B is VV sine 90, and sine 90 is 1, so we can write. So F equals to QVB. This is the force. Due to that force, the particle deviates. Otherwise, particles should follow this direction. Na? Due to the presence of the magnetic field, the particle deviates through this detector. Approaches to the detector. Okay, so now we can see this is the deviation, right? So it is a, we can think like this. So it is a circle of radius r. Let me draw properly. Okay, we can think like this, this is a circle. Okay, and the radius of the circle, let's say r. The radius of the arc, actually not the circle. Okay, let's say we are writing the circle. Actually this is a arc of the cycle. Okay, radius of the circle is r. So we can write the force qvb should be equals to mv square by r. Okay, where r is the radius. So if qvb equals to mv square by r, so from here we can also write q by m is equal to v by br. Okay, and previously we obtained that q by m is equal to v square by 2b. So now if we square it, what happens? We can write v square by b square r square. And previously what we obtained, that q by m equals to v square by 2b. So now if we divide that, this is equation 1 and this is equation 2. Now dividing equation 1 by equation 2, what we obtained, that q by m equals to 2v b square r square. Okay, this is the, here we know this b is a magnetic field. We know the value of the magnetic field. This is the radius. This is also known to us, and this is the voltage, not voltage. The voltage difference, this is also provided by us. So we know all the parameters. So from here we can actually identify the value of q by m, and this was actually done by J.J. Thomson, and he obtained that this value actually is 1.76 into 10 to the power 11 coulomb per kg. This is the value of the q by m. So till now we don't know the what is this particle. We know that this particle is negatively charged particle, the particle of the cathode ray, negatively charged particle, and the features, the characteristic of the particle is this: the q by m, q is the charge and m is the mass of the particle, is 1.76 into 10 to the power 11 coulomb per kg. Else we don't know. We actually don't know the value of q and m. Actually, we know the ratio of q and m, but we don't aware of the q and m separately. Okay, this experiment was done by actually J.J. Thomson, as I said, at 1897, I guess. Yes. Okay. So at 1897, actually, this particle was discovered, and this particle was named as electron. Okay. How this particle actually named as electron? Till now we don't know the q of the electron and the mass of the electron. Just we have identified that q by m is 1.76 into 10 to the power 11. Okay. See, in that period, 1887, and at similar period, similar kind of experience was also occurring, also done by several scientists, and found that not only this in this cathode ray, also some other experiment also, similar kind of experiment where the ultraviolet ray is actually let's say okay, ultraviolet rays irradiated on some plate, then also this type of flow particles occur, and for that particle also q by m is the same q by m achieved. Also the velocity of, in that case, the velocity is less than this cathode ray, but the q by m remains same, which actually indicates that the particle is the same. The particle in cathode ray and the particle in case of other experiment in that time, these particles are the same particle, and this is the fundamental particle of any matter, because if we change the matter of that electrode, that plate, the q by m remains same. That means we can take any matter, any metal, but the emitted particle, the particle emitted from that electron, is always is the same particle, because the q by m, the ratio of charge and mass, remains same. So this particle is a fundamental particle of any materials or metal. So this particle is named as electron. Okay. Now later, after photoelectric effect event in 1913, the scientist, American physicist actually, Millikan, the famous Millikan's oil drop experiment, he did that oil drop experiment, and in this experiment, what he identified that um, okay, we don't get into the oil drop experiment. We just need the outcome of that oil drop experiment. After performing the oil drop experiment, he make a precise measurement. Okay, and he found that the charge of an oil droplet was always an integral. The charge of an oil droplet, let's say Q, is always of integral n into 1.602 into 10 to the power minus 19 coulomb. N is integral. N may be 1, 2, 3, and so on. So this is the charge of oil droplet he found. Okay, N into this. So from here he conclude that, so this is the charge of that elementary particle electron. That elementary particle which we named as electron. Okay, so this the charge of now this is the charge of electron, E, we denote as EQ of electron. So this is 1.602 into 10 to the power minus 19 coulomb. And we know the Q by M, or we can say now E by M. What is E by M? E by M is 1.76 into 10 to the power 11 coulomb per kg. So from here easily we can evaluate the mass of the electron also. So okay, through these two experiments actually we actually evaluate the mass of the electron and the charge of the electron. So this is the discovery of electron. Now okay, up to that everything is fine, but now something occurs. Okay, we'll get into that. Up to that everything is fine now. Okay, now we'll discuss the procedure of electron emission. We said na that contemporary some research also, some experiment also was occurring, that ultraviolet ray radiation, something that. So not only through the cathode ray, but also some other experiment, the presence of electrons was identified. So we'll study that. Okay. Okay. Before that, we know about electron volt. What is the electron volt? If there is a like this, let's say, and this is our discharge tube. Okay, this is negatively charged, this is positively charged. Now we know that this cathode ray is actually flow of electron. Okay, if we give the 1 volt, voltage difference is 1 volt. Okay, and we know Q is the E. This is the charge of electron. Okay, so we can now write Q into V or E into V. E is the charge of electron, V is the the voltage difference or potential difference. So this E into V equals to, this is called 1 electron volt. So this is obviously unit of work done. So now we can evaluate, this is 1 electron into 1 volt. So now charge of 1 electron, what is the charge of 1 electron? We know that the charge of 1 electron is 1.602 into 10 to the power minus 19 coulomb. Okay, and this is 1 volt. So this is 1.602 into 10 to the power minus 19 coulomb into volt is joule. So 1 electron volt is 1.602 into 10 to the power minus 19 joule. This is the unit of electron volt. That means if we give a potential difference of 1 volt and 1 electron is moving, then the energy of the electron will be 1.602 into 10 to the minus 19 joule, or it is called 1 electron volt. Okay. Okay. Yes. Now we will see the electron emission procedures. How electron emits. Okay. How electron actually emits. Electron emission procedures. We know that metals have free electron. Okay. We are now familiar with that. Metals are conductive actually because the presence of free electrons. Metals conduct. So metals have free electrons. So now uh, let let me first draw the setup. Okay. No. I have to draw. Okay. Here is a hole. Here is an electrode. Here is another electrode. These two electrodes are actually connected. Okay. Okay. These are connected to actually the voltmeter. So we can. This is the voltmeter. Now through this window, through this hole, the light radiation. Light is actually radiated to this plate. Okay. To this plate. Okay. When the light radiated to this plate, what we can see, sometimes actually the deflection of that voltmeter occurs. What does that mean? That means due to irradiation of that light on the metal plate, this is the cathode, actually the metal plate, not the cathode, sorry, and not cathode, this is a metal plate. So due to irradiation of that light, here we can have some deflection in the voltmeter. That means flow of electric current occurs. How flow of electric current occurs? That means there is some flow of electron. Then only we know that we can have the electric current. So due to radiation of the light on metal plate, some electron actually emitted from that metal, and some electron emitted from that metal, and it here through this plate, and after that it flows in that direction. So we can have a flow of electron, and that's why there is a deflection in the voltmeter. Okay, so this phenomena was also observed, and this particle is also electron. We can identify by the Q by M ratio. If we measure the Q by M ratio, then we see that the Q by M ratio is the same as the electron. So this particle is obviously eventually the electron. Okay, so now we have to describe this phenomena. What is happening here? Okay, due to radiation of light, we can have the flow of electron. The electron is emitted from the metal, and it's give us the deflection in the voltmeter. So now here one term is important. Here, this is the work function of metal. What is the work? Okay, always if we write that, it is not necessary that there will be a flow of electron. Okay, there is some condition. So what is the definition of work function? That is the minimum energy required by an electron. Not we should write, because it is okay, it's electron to escape from the metal surface. That energy is called work function. That means this is the metal plate, light is irradiated here, and from here electron is emitting. But in metal, if we zoom it, so here is the electron na? So here is the electrons are here. So when we irradiated the light, the electron is emitting. That means some electron is bound to that metal. So we should give some amount of energy so that it can escape from that metal. So that amount of energy is called work function. This is denoted by phi. Actually not phi naught. This is called work function phi naught. Okay, and this phi naught depends on the metal. This is the characteristics of the metal. It varies if we change the metal. So phi 0 is the work function. Here, from here the table is given in that NCERT book. Then for cesium, the work function in electron volt, obviously, for cesium phi 0 in electron volt is 2.14. This is the least, and for platinum, this is the highest. That means for cesium, electron is loosely bound, but for platinum, it is very strongly bound. That's why it needs much energy to escape. Okay, so this is called work function. Now, how we not only just irradiating light, there are some other procedure also by which we can also make this kind of effect that we can make that escape the electron from the metal surface. There are some more procedure. Okay, like that, first is fermionic emission. Okay, what is, from the name we can identify there is something related with the heat. If we give the sufficient thermal energy of that electron, that metal surface, this is the metal surface. If we give the sufficient thermal energy, I'm not drawing the same thing. Okay, like this. Then after giving the sufficient thermal energy, if there is a reflection in the voltmeter, then we can say that due to that thermal energy, using that thermal energy, electron escape from the metal surface and it approaches to another metal surface, and that's why there is a electric flow. So this is actually fermionic emission. Okay. Similarly, there are some other types like field emission. If we give here a strong electric field, if strong electric field is provided, then also the flow of electron, the electron can also be escaped from the metal, and we can have the flow of electron. So here the order is given 10 to the power 8 voltmeter inverse. This amount of electric field is provided, then okay, let me write 10 to the power 8 volt per meter. In this order of electric field is provided, then we can have the flow of electron. This is called field emission. And another one is photoelectric emission. What we discussed actually, if ultraviolet, basically ultraviolet light is irradiated to the metal surface, then flow of electron occurs from the metal surface, electron actually emitted, and it approaches to other. Okay, we'll discuss in details, but using that light, electron escape from the metal surface, that is called photoelectric emission. So there are some 3 types of emissions, and in case of photoelectric emission, that electrons are called photoelectron. Very important, photoelectron. And overall, this phenomena, if we irradiated light and electron is escaping, this is called photoelectric effect. Okay, this is called photoelectric effect. Now we'll discuss photoelectric effect in details. Let me start today. Just start photoelectric effect today. We'll not discuss details today. We'll just start it. Photoelectric effect. Okay. So first, Hart's observation. Okay. Hart's observation. It was in 1887. Okay. So what Hart's observed? He observed that high voltage sparks. Sparks means the presence of electron. We can see like, you can think like that. Across. Okay. First, we have to just draw the setup. Similar kind of setup also taken in his investigation. He saw. Okay. Let me just. Okay. Like this. Okay, and one important thing, photoelectric effect was discovered by Hertz actually, not by Einstein. Einstein explained the photoelectric effect, but at 1887, this photoelectric effect was actually discovered or discovered by Hertz during some electromagnetic wave experiments actually. So the setup is not like this actually, so we should not draw like this. Okay. What you observe that when light is irradiated on metal surface, electrons come. Not electrons, because at that time also at 1887 we don't aware of the electron. At 1897, as we discussed before, J.J. Thomson actually discovered the electron. So what is the light shining on the metal surface? Something happens actually when we irradiated light on the metal surface. Some charged particle emits from that metal surface. We know that is electron now, but in that time that was not known that that is the particle is electron. So he observed that when on a metal surface light falls, some particles, charged particle actually emits from that metals. Okay, and that's why the metals become positively charged. This is metal, it is neutral. If light shines on the metal, what happens? Some particle actually emits, and these particles are negatively charged particles. So that's why what happens after emitting that particles, these metals remains become a positively charged metal. Okay, so what mean that means that that particles, negatively charged particles, are actually free in nature, and it was just bound to that metal. When we irradiated the light, this light shines on the metal, that light provides some energy, and that's why that particles escape from that metal, and metal become positively charged, and that particle escape from that metal surface. So this phenomenon was observed by Hertz actually, but sufficient energy should be required, otherwise the emission of the particle will not occur. Okay, similar kind of similar kind of observation was also observed by Alva and Leonard. This is very much important. Leonard's observations. Okay, so Leonard also the setup. Okay, that setup. Wait, let me draw the setup for Leonard. This is the actual setup Leonard used, like this. My drawing is not that good. That it is cathode, it is anode. Okay, so from here the light is coming. Okay, okay, like this. So this figure also given in the book. Okay, that means here is the voltmeter. This is the Buddha. Okay, so if there is a deflection, there is a flow of electron, this voltmeter deflects. This is the setup of Leonard, as we discussed. This similar kind of setup, this setup actually used by Leonard's. So Leonard's actually obtained that what he observed when light falls, when the not he used the ultraviolet light, ultraviolet radiation. Okay, when ultraviolet radiation was irradiated on the metal surface, these are emitted. So this was observed by Leonard. Okay, yes. So when electron approaches to anode, and there will be a flow of electron, that means electric flow of electric current, and obviously voltmeter reflects. The same experiment we discussed, that experiment was actually done by Leonard. Okay, and what's the Hall? I think this is Hallward. So Hallward, what he did, that he took a negatively. Okay, here Hertz did a neutral plate, and after emitting electron from that negatively charged particle from that plate, the plate becomes positively charged. Hallward actually take a negatively charged zinc plate. This is negatively charged. Okay, when lights irradiated on this plate, again the negatively charged particle emits. That means it becomes gradually neutral, and after again if we irradiated shines the light on that metal surface, zinc surface, again the negatively charged particle emits and it becomes negative. Now it's become positive. Okay, so through this experiment, it is concluded that the particle emitting from the metal surface is negatively charged particle, and this is the fundamental particle. Later, it was identified that this particle is electron, and this particle has mass charge is 1.6 10 to minus 19 coulomb, and mass is 9.3 10 to minus 31 kg. Okay, so this was discovery of the photoelectric effect. This is the photoelectric effect, because when we impose that light on the metal surface, electric current occurs. So photoelectric effect. Photo means the light, and electric means the electric current. So this is actually the photoelectric effect. Now, it is not always that we obtain electric current. Okay, there is some certain frequency of the wavelength range. Okay. Then only we can have that electric current. So that frequency is called threshold frequency. What is the threshold frequency? This is very much important. Threshold frequency, right? What is the threshold frequency? This is, let's say, new. New is new threshold. If the light, the frequency of the light is greater than this new threshold, then only photoelectric effect occurs. That means then only electron escape from the metal surface and it gives us the electric current. Otherwise, if it is less than the threshold frequency, then there is no photoelectric effect. There is no flow of the electric current, no deviation in the, no deflection in the voltmeter or the ammeter. Okay, so this is the minimum frequency which is required to have photoelectric effect. This is called the threshold frequency. Okay, and it is different for the different metals. That means this is the characteristics of the metal. Okay, here some example also given. Yes, for the in general, ultraviolet ray is used for photoelectric effect. We know that the for ultraviolet UV, for ultraviolet ray, we can have this photoelectric effect actually in general, but for some metals like here given the names, the alkali metals like sodium, lithium, potassium, rubidium. For this, actually, we can have the photoelectric effect even in the visible range. If we irradiate the visible light, then also we can have the photoelectric effect. We know that for visible light, the frequency of visible light is all actually the less than the ultraviolet. Okay, we know that. That means for sodium, lithium, potassium, these type of metals, the escape energy is less. Escape energy is the wave function, the work function, as we discussed before. The thing is very clear. Light has energy, okay, and frequency as well. And the electrons of the metal require some work function. There's some energy, some limiting value of energy by which that is bound to the metal. If we give more than that energy, then electron escape from the metal. That is called work function phi 0 or phi naught. What we say. Now there is some limiting value of frequency, the minimum value of frequency. If we give, if we impose the light which a frequency greater than that value, then only we can have that photoelectric effect. That means then only the electron will escape from the metal surface. Okay. If we give if the frequency of that light is less than that minimum frequency, then there will be no photoelectric effect. It clearly means that that frequency actually provided that minimum bound of the energy by which the electron is bound to the metal. Okay, then only if we give the frequency of the light is greater than that frequency, then that light is capable to provide the energy greater than the work function. Then only electron is escaping from the metal. Here for visible light, the frequency is less than the UV light. That means for this kind of metals, the work function is less. That means electron is loosely bound. That's why the less amount of energy is required to escape. So the work function is less. That means less amount of energy is required. That means the threshold frequency is also less. That's why visible light is capable to make photoelectric effect. Okay. And as we discussed, this electron is called photoelectrons, and this total effect is photoelectric effect. So this is the threshold frequency, but this threshold frequency, as we discussed, is clearly a characteristic of the metal. If we change the metal, as we can see them, for this kind of metals, the photoelectric, it is visible light can be photoelectric. Okay, that means if we change the metal, the new threshold also changes as the work function changes. So the metal, if we change the metal, what happens? Phi 0 changes. That's why the new threshold changes. Okay. So next day we'll discuss in details the experimental study of the photoelectric effect. We discussed today also the experimental study, but we did not discuss the experimental result. Next day we'll discuss the experimental result and we'll also analyze that and the stopping potential and the other things we'll discuss in next day. So now to summarize today's class, what is the summary? Summary is that first, cathode ray. What is the cathode ray? Cathode ray is the flow of some negatively charged particle. This was in 1879. It was in not 79, I think at 70. Okay, and at 1879, it was identified that it is flow of negatively charged particle. And J. Thomson at 1897, through that experiment, we discussed that experiment, Q by M or E by M was discovered, and this particle is named as electrons. And later, Millikan, not Millikan, Millikan is another scientist. At 1930, he identified the charge E of 1.60 to minus 19 coulomb, and from here we can also evaluate the mass. This was the history of the electron as we discussed. And simultaneously at 89 to 9, okay, at that contemporary period, because the timelines are not strictly mentioned, so what occurs that Harge experiment, Harge experiment 1887, it was discussed that when light is irradiated in metal, that electron, that was in that time that was not known as electron, that negatively charged particle, some negatively charged particle is irradiate, it's emitting from here and it becomes positively charged. After that, Hall's experiment, okay, he took a negatively charged zinc plate, and after that, after emitting the negatively charged particle from here, it becomes neutral, and after that it becomes positive. And at last, the Leonard, the most important part of that time, that Leonard actually give that setup like this. Here is some voltmeter, and through here light is emitting here, and flow of that negatively charged particle occurs. Okay, so this was the Leonard's experiment, and from this Leonard's experiment, he identified that there is some threshold frequency, new threshold. If we give radiation, if we irradiate the radiation having the frequency greater than the new threshold, then only this photoelectric effect occurs. This is called photoelectric effect. And there is some Watt function. We also discussed Watt function phi 0 that is associated with the metal surface. Metal, actually, this is the property of metal. Okay, by which the electron is bound to the metal. Okay, so this is the summary of our today's class. Next day, we'll discuss results of photoelectric effect. Okay, photoelectric effect actually. Today we just discuss the experimental setup of photoelectric effect and the observation. Next day we'll discuss the results part of the photoelectric effect and the stopping potential and other stuffs, which stuffs. So this is today's lecture. Okay, so should I stop now?